Right. Good morning, everyone. Let's get started with today's class. I have a few things I want to share with you before we get into the actual content of this class. I ask for those of you online, turn on your cameras so we can get going here. All right, so one thing that I want to just remind you all is this class starts at 9:30. I do expect all of you, if you're coming to class, be here before 9:30. This is mostly because if you do get in late, you may be able to catch up, but you may have to disturb your partner or colleagues to do that. And so to make sure that, I respect, especially those in person, that we respect those that are already here and following along, that they do not get disturbed. I do ask you to get in here on time. I know life happens, things happen. Feel free to reach out to me. I'm very flexible and I'm very accommodating of any needs, but I do expect you to be here on time otherwise. So I've been flexible up until now, but I'm gonna start asking those that come in late in person, at least in Athens that I can see, to excuse if you're getting late, so you don't disturb other people in the class. All right. So last class, we basically wrapped up with where we were talking about blocks, fixed and random. You did pair, if you were in person on your campuses, you had a chance of pairing with somebody to go through that together. We did not have time to really talk about what you found out. So you did submit your answers for that assignment. You're going to be graded on those. But I really wanted to ask for maybe one person from each campus to just share what they found, or maybe a group, or maybe a representative from a group in each campus. I guess that's what I was trying to say. So maybe we can start here with Athens. Anyone would like to share what you found as far as, like, if you observed that the results were different between blocks fixed and block random and what you observed? Anyone here would like to share what they found?
We found that for ANOVA tables, we have used, so the interaction in fixed effect tables, they were lower as compared to the other model that is random effect model. And for standard array, they were higher in random effect model
Okay.
as compared to mixed effect model. And for
Okay.
that situations, like they were almost same for all both the models.
Okay. So Amandeep here in Athens said that the p-values of the random effect were,
Fixed effect were lower.
the fixed effect were lower, the means were the same, the standard errors of the mean,
Were higher for random effect.
the means were higher. Really?
Yes. No,
The standard
error.
Yes, the standard errors were higher, yes. Okay. And separation was the same. Okay, maybe in other camp. So I don't know if you were able to hear that. Let me just repeat them. So p-values on fixed were higher. The E means were the same. The standard error was higher for the random effect.
Yeah.
And then lattice separation was the same, right? Did anyone find maybe different results?
I think the EM means were not same. They were, I remember the figure, one was 307 when one was 330. And I think for fixed it was lower. For random it was 330.
You mean the means or the standard error?
So there was also a question about the EM means.
Right. So
One part was about that.
right. So, but are you talking about the means being different or the standard error of the means being different?
I'm actually talking about the means, the column that I saw of the EM mean that we extracted.
Okay. So in our case, the EM means themselves should not have been different. Did anyone else find the EM means to be different? Okay. Well, take a look at that, Umar, on your side, because the EM means themselves should be the same, but the standard error of the means is what was different.
Okay,
Yeah,
I'll look into it.
Yeah, somebody else?
Right. I think he's talking about the standard error. So for the fixed effect model, the standard error was 307. But when you change it to mixed effect, like the random effect, then it increases up to 330. But the estimated marginal means, they would always be the same, whether you keep it as a fixed effect or mixed effect. So at least that's what I got, and that's what I understand from the lecture, but I might be wrong.
Perfect. Well, thank you, everyone. I think, yeah, I think these three sharings are probably enough. And I do want to show you here. So if you read the paper that I had as a reading assignment, I'm going to just go ahead and open that. That is a really great paper to kind of help us understand this. Which was a reading assignment on February 11th. So this is I'm not going to go through the whole paper, but if you ever faced with this question, should you treat as random or fixed? This is a very good applied example or a paper that has some really great examples. What I want to bring us to is this table right here. So this is the key table that is basically explaining what you found in your assignments. So if you have a randomized complete block design without missing data, which is what our case was, if you treat blocks as fixed or as random, as we were playing around with, your treatment means will be the same. Any contrast that you do are going to be the same. The estimated error variance is the same. The estimated standard error of treatment differences, and there, notice that treatment differences is the same, and I'll tell you a little bit more about that. And inferencing contrasts, which is just like, so pairwise comparisons is one type of contrast, are the same. The only thing that is different in a randomized complete block design that does not have missing data is the standard error of a treatment mean. And here's why. If you treat blocks as fixed, the standard error of a treatment mean, so your EM mean standard error, is going to be sigma square of the error or the residual divided by number of blocks. For that same calculation, if blocks are random, there is that sigma square of the error or residual plus the sigma square coming from the block divided by block. And we talked about this when we on the lecture that the way that the error is calculated is differently is from these two sources, because one just had the residual error, so the fixed block just has the residual error. The random block has both residual and block variance into that estimation. The thing is that the reason why only the treatment mean standard error is affected and not the pairwise comparisons is because when you're doing any type of contrast or pairwise comparison, the block effect is still there, but it cancels out because you're comparing two things. So basically, your lattice separation in this case should not have changed, even though the overall error is larger, but it's canceling out when you're making a comparison between two means. So this is basically what I was trying to get us to on an applied case. And then, you know, if you read the paper, maybe that makes more sense now since we did a hands-on as well. However, and there is a big however here, this only applies if you have randomized complete block design with no missing data. If you have incomplete or unbalanced blocks, this does not hold. The reason for that is because now a lot of things are going to change, even your means, because now if you have missing data or incomplete block, which is a type of design, we're not going to go through that in class, but it is a type of design. Then now both the mean and the errors are being estimated differently for different blocks, and that has an impact on not just the individual mean standard error, but on the mean effect, on the mean values, on the pairwise comparison errors, and so on. So I just wanted us to kind of connect what we did in class with what this paper was describing. If you ever have some of these more complex examples, this is a great resource for you to get some tips on how to treat, if you should treat your block as random or fixed in other contexts. All right. I want to talk about grading assignments now. And so this is basically for the CRD assignment. Amrinder and I have been working on grading those. And I have some overall comments for you to make sure that you get the most out of any assignment opportunity, that you get the most grade you can, right? So a few things that we noticed on the CRD assignments that not all of you did because it was extra credit, it was optional. So a few things I want to point out, that a few places where some of you lost points that could have easily been avoided. You could have easily not lost those points. So one point is looking professional, right? So this is going to apply to every assignment you submit as an HTML. If it's not looking professional in the sense of, maybe after rendering, things were not looking right, you didn't have your structure come out on the table contents appropriately or correctly. Maybe if you had those packaged loading messages, you're losing points there. Easy fixes, you don't have to lose those points. Also, every time that I ask you a question and you're giving me an output, I do expect you to tell me what you're seeing, to interpret that output. As we saw, we have to be able to interpret. If you just gave me the plot, you did not write any sentence saying what was going on, you just lost half points of that question. So do not do that. Easy, just a quick sentence, just telling me what you're seeing. Very simple. Do not miss those points. Give me an interpretation and don't lose those points. Something else that we observed is, so if you remember on that ANOVA table, I believe the main effects were significant, but not the interaction, which is different from what happened in class. So as we talked about in class, we use the ANOVA table to decide how we break down names and make pairwise comparisons. If you gave me the pairwise comparison of the interaction, you lost points because it should have been the main effects of both nitrogen and potassium separately, because just the main effects were significant. So that perhaps is one that, it's not just aesthetics, it's really more you knowing what to do when you're facing these ANOVA tables and deciding how to show your means. But it's a simple yet key concept, because it's going to trickle down to your own research when you are writing your papers and deciding how to show data. So remember that we always start from the bottom of the ANOVA table, looking at the most complex terms. If that most complex term, if that is an interaction, is significant, you would break down that way and do that pairwise comparison. You could still, if you wanted, say that the mean of nitrogen by itself, the mean of potassium by itself vary from this to that. But that should not be the focus of our discussion, because the means of the main effects alone do not represent the whole picture if the interaction is significant. However, if the interaction is not significant, then you would show main effects like you would have on the CRD assignment. So if you show me all three, you probably still didn't get full points, because you're just showing everything you can. So of course you're going to get it right. But if you only show the interaction, then you lost points there, because that was not the proper way of showing for the assignments. So that was another one. One thing that we notice on the professional side as well is when you're rendering, and we talked about this of adding 2 white spaces to break line. If you rendered and then for some reason that line break didn't happen, now all of a sudden your heading level is not a heading level anymore. It's just text connected to a previous sentence. That's also something to watch out for. What else? What am I forgetting, Amrinder?
Like some is submitting PDF format rather than HTML.
Yeah, please submit into HTML format just to make it easier for us to grade as well, because we can easily navigate the table of contents on our side. So please do that.
Please don't delete any chunk or things you provided.
Yeah, thanks for the reminder. Yeah, so another thing was also, all of these assignments, I'm going to be providing you some scaffolding of what I'm expecting for you to do. Please do not delete that, because that helps us to grade. Like, we have a lot of people to grade, and these assignments can be lengthy and complex. And so that really helps us on the grading side. If you delete the scaffolding I'm giving you, it makes it harder for us to grade. So you lose points if you do that as well. So overall, very small things, but something that you're going to notice in all the assignments that I give you is I like to give you instructions so you know what I'm expecting of you to turn back to me. So if I tell you to do something and you don't do, that's an easy way for you to lose points. So if you don't want to lose, silly points, go through your instructions maybe 2 or 3 times if needed. I know sometimes I can provide a lot of instructions and you may feel overwhelmed with that, but it's just to make sure that you're providing everything I need to give you the most points that I can. Yes.
Yes, okay. So sometimes for the HTML, it might appear really nice in my computer. Once I upload it, or I download it, it just appears like so weird. And that's why I think a render is asking for the PDF. And because the HTML, it might change from computer to computer. No, I'm asking for HTML. Yeah, with PDF, it's scrolling, page is becoming very, very active. Okay, because basically when I try to download my CRT, it just appears like this with no picture. There is some problem with
Okay. So let me just say that online as well, so everybody is up to speed. So Charles is saying that, and I'll be with you, Shakir, in a second. So Charles is saying that when he renders to HTML and then maybe he opens on a different computer, it looks like unformatted, like it doesn't show the plots, it doesn't show the structure, any of that, right? So that's what Charles is saying. While I'm looking into Athens here, anyone else is having a similar issue or had a similar issue when rendering? Okay, anyone online had a similar issue where it looks good when you render, but then if you try to open elsewhere, the figures don't come with it or something like that?
Yeah,
Well,
I
it
had
didn't
similar
try
issue.
elsewhere.
Okay, hold on. Let's Shakir, go first.
So yeah, when I open it from the code folder, it just opens just fine on my side. But if I download the assignment and open it from the downloads folder, the graphics is gone. So,
Okay.
but when I open it from the code folder, like the R project folder that I created, like I'm following your instruction, it's just fine. I can show you sharing my screen.
Oh, that's
So,
okay. That's true. I believe you. Yeah, okay.
So my question was, I don't see a grade for my CRD assignment. The grade has not been uploaded.
I don't think we posted the grade yet. They've been graded.
Okay,
Haven't posted yet.
got it. Thank you.
Thanks. Kumar.
Yes, so I was a bit confused in 2 things that you mentioned. So one was like make the presentation look professional, and the other one was do not delete the instructions. So I remember there were some instructions which were not relevant to grading, I guess, which were like right after the plot, final plots. So I'm just curious, like for future assignments, if if you, in order to make it more professional, if you take out those instructions, just a few sentences which you're saying, like write 1 sentence to explain.
No, so everything I'm giving you, just leave there. You can add stuff, but you should not delete anything I'm giving you.
Okay, got it. Thanks.
All right. Any other quick questions about the assignment and the things I'm telling you that you may have lost points because of?
Yeah, can I ask a question?
Sure.
For the letter separation, what I did a facet by comparing the nitrogen rates within each potassium rate. So is that I think what do you think about that? Is that a valid approach? So I'm not
So
comparing.
that would be basically an interaction type of comparison, right? So in this case, because the interaction was non-significant, you would just look into nitrogen by itself, just look into potassium by itself.
Okay, thank you.
All right.
Dr. Bessos, I faced one issue during the assignment is that uh, whenever in a chunk we are writing something after that small r that we are doing the wrangling or some other name, I followed your instruction changing the name and those things. But when I was rendering, I was having an error that there was no browsing or something. But then I saw the issue created in the website, and there was one solution that don't uh, write anything after that R small r thing in a chunk, and then it comes out fine. So uh, I I just followed your instruction in the class, and you write something, you render it. It was fine for you, but it was not fine for me.
I think
That's
perhaps what happens is when it's rendering. So what I do, I always give like a short title to each chunk, and that title is different from every chunk. And I think if you're rendering and you have two chunks with the same title, then that's when it gives an error. Yeah. So I guess I never tried to not name all of them like what you're saying, but if that is a solution, then great. Yeah, the main thing, so when you render, what's gonna show up on the table of contents are not the chunks. It's gonna be just the heading levels 1, 2, 3 if you have. So I don't really care if you name or don't name your chunks. As long as you can render and you keep the heading 1, 2, 3, whatever it is, then that's sufficient. All right, so I'm gonna keep moving here just to make sure that we get to other topics that I want to cover today. If you have more questions, feel free to, if it's something very specific to your grade, once we post that, we're also gonna post comments to let you know where you miss points. So if you have questions about that, you can email Amrinder first or email Amrinder and CC me. But if it's something more general, you can then open an issue on GitHub. Yes, Comfort.
Yeah, I just wanted to know how you're going to address the point that Shakir made because I also just tried for my hand to download the HTML for my ELC and it's not looking like how I uploaded it. But I know that when I sent via email and you download from email, it's kind of gives the good format. And I noticed that the when you download from ELC, the size has already reduced compared to what you actually uploaded or what is showing on ELC. So I don't know.
Okay, so let's do this. I'm gonna ask, so let's say if you know that when you download yours from ELC, it looks different from the one that looks on your computer, and it does not look professional in that sense, then if that applies to any of you, it means you probably lost a few points on professionalism, on the looks of it. And if that's the case, then let's try something else. Because if that happened to you, specifically to any of us, to any of you, email Amrinder your HTML. So let's try that by email, and then Amrinder can just quickly check it out. So what we're looking for in that is just to look that's professional. We're not regrading the whole thing. So if you did something wrong in the first place, we're not gonna regrade the whole thing. It's just about the professionalism and the fact that perhaps ELC is giving us a different version than what you uploaded on the professionalism side. So if you think you're affected by the ELC version not being professional, please email your HTML to Amrinder and CC me. And I'm gonna reconsider that just for the professionalism side of it, not the rest.
The thing is, I haven't even seen my grade and I don't know what it looks like at your end, but because when you download from ELC, you're just saying white and black and they're all in tiny texts. So it doesn't even look good at all.
Yeah. So we're gonna probably post the grades for that today. So they've been graded and Amrinder was writing comments on everyone. So if you lost points due to whatever reason, whatever question, there's gonna be a comment there to let you know. And so if you have a comment of, did not render professionally or whatever, and you know that you did, then reach out to us and we can fix that.
Thank you.
All right. Thanks, everyone. Okay, so that was it about that. Oh, and also, something for you all to keep in mind. So that was one extra credit assignment. We may have another one here as well that's going to be extra credit because it's something that perhaps some of you want to learn, others don't care. So we're going to have another opportunity for extra credit assignments. What I want to let you know, the way that I'm going to treat extra credit assignments is they may replace another assignment grade if the extra assignment grade was better or higher than one that was mandatory. That's how I'm going to use. Meaning that if you do an extra assignment credit and you have a bad grade for whatever reason, that is not going to impact your grade, but you're also not going to be able to use that to replace another grade if you don't have a worse grade than that, right? Meaning that if you're really putting the effort into extra credit assignment, make sure you check the instructions, don't lose points on silly things that you can easily avoid, and make sure that that really goes to your benefit. So I just wanted to say that. Okay, I think that's all I had for this part. We're gonna have more assignments. Some of them are gonna be mandatory, some are gonna be extra credit. Always make sure you check the instructions that I give you and follow them. All right, so we wrapped up. So we've seen completely randomized, or I guess some of you saw completely randomized design if you did the assignment. We saw randomized complete block design with blocks random, fixed and random. Now the next design we're gonna see is gonna be split plots. This is a very common design in agriculture as well. And it's one that probably some of you may have on your research. So we're gonna cover that and understand how that is different from just a randomized complete block design, how it changes from the planning side, from the randomization side, from the implementation, and especially from the analysis side. There are some really key differences there. So we're gonna first go through the lecture, and then we're gonna have our actual code exercise. So let me pull up the lecture. It is on our website. If you wanna follow along on your side, you're welcome to do that. Otherwise, you can just watch online. All right, so the goal of this lecture here is for us to explore some very key concepts around split plots. Things like different sizes of experimental unit. This is a very key component of a split plot. Treatment randomization, how does that happen and how is it different from just a randomized complete block design? We're gonna take a look at the effects model to create some of that understanding of how this, how is different from previous models. We're gonna take a look at the ANOVA table, and there's gonna be a very key difference here for us to be aware of and to think of. If you ran a split plot on the field, but then you analyze that with the wrong code, so with a code that does not represent a split plot structure, what are the implications? And those are the goals for today. So very quickly, we're still keeping the same motivational example. So we have our two-way factorial, nitrogen rates, three levels there, 0, 100, and 200. Potassium rates, 3 levels as well, 0, 30, 60. We have all combinations between them. So we have a total of nine treatment combinations. And that's our treatment design. Something that's kind of interesting to think about is, so treatment design is like this, right? It would be what answers your study questions. Now, experimental design takes care of your lack of homogeneity of experimental material. So CR, completely randomized design, randomized complete block design are all experimental designs, right? Now a split plot is kind of has like a foot on each, because it's gonna help you to accommodate your treatments in a way that makes sense, and you're gonna see why in a second. So, but also it has your treatment design in it, but it also has implications on how the errors are computed, which is basically what experimental design does for us. So a split plot is kind of like has a foot on each one of treatment and experimental design. All right, so when is split plot needed? This is very, very common when the levels of one treatment factor need more or less experimental material than the levels of another treatment factor. So for example, and I do realize that this example is perhaps very easy to understand if you're thinking from a field crop perspective, and I will try to provide some different examples that are applicable to other disciplines. But basically, so if we think that, for example, if I were to tell you that potassium treatments are applied with a 12-row spreader, what do I mean by that? So when we plant row crops, we have I mean, normally we have a planter that has planting units. And each one of those planting units, as the tractor is moving across the field, is planting one row, right? So we have rows. I would imagine you probably have seen crops on the field that you know they're grown in rows. So in this example here, what if potassium treatments are applied with an equipment that the minimum size that that equipment applies is a 12 row? So it needs 12 rows for a single treatment. And nitrogen rates are applied with a 4-row equipment. So while the nitrogen rate application happens on 4 rows, the potassium happens on 12 rows. So, and that's a limitation from the equipment itself. You cannot make the potassium spreader to apply in less rows. That's just the size of it, right? It's just going to be 12 rows. So we see here that we have a mismatch between how much space I need to apply potassium and how much space I need to apply nitrogen. This is a very, very easy example. Something that perhaps could be, well, I'm not sure if I can think right off the bat an example in food science. Perhaps I know we have a handful of students from food science. Does anyone in food science have had a split plot design or have read about in a paper that you would be able to share an example from that perspective? Okay. Yeah, so I guess we don't have a good example from food science, and I'm also cannot make up one from the top of my head here. But
I
anyway,
can give one.
hey, yes, go ahead.
So for example, you are trying to bake a cookie. It's a very simplified example. And you are using incubator of some sort or baking machinery of some sort. And you can use only like two trays of cookies, but you have like 10 or 20. And each of the levels of the incubation has different types of temperature. So in that case, you're restricting randomization based on the batches that you were inputting and outputting. So since you're restricting the randomization based on this, that would be a split plot.
Nice. That's a great example. So your oven is larger than the trays that would be maybe, I don't know, an ingredient difference in treatment, for example. So you could have, let's say you have 3 ingredient treatments on cookies, and then you're testing them on baking them at different temperatures or maybe different times, where your oven is larger and it can accommodate multiple trays. That would be a great example as well. Yeah. Nice. Thanks, Rakir. All right. So in our example, we're going to give you some pictures to kind of help us illustrate how that will look like on the field, or at least on this example here of potassium needing larger area than nitrogen. So for example, this would be a spreader. So it's basically spreading dry fertilizer. It's just throwing that fertilizer out from the back of that spreader. And the range that fertilizer reaches is 12 rows, right? So there's no way we can reduce that range. It's just set by the equipment itself. However, for nitrogen, we have this smaller equipment that's applying liquid nitrogen on 4 rows, right? So this is how this example applied to us, to our case study, will look like. So we have this mismatch between how much area we need for one treatment factor compared to another treatment factor. Another example here that's very common in agriculture, think of any treatment, if you're applying on the field, any treatment that requires larger area in any sense. So another great example is irrigation. Normally, irrigation happens on a larger piece of area, and it's hard for you to decrease that size just because the irrigation equipment is so large. So you require a larger area for the irrigation treatment. Let's say you have no irrigation, full irrigation, and twice as much as you need. So normally irrigation requires more area than whatever else you're testing with it. And so that would be another example where split plots are very commonly used in field ag. Yeah, sorry, Phil.
So the example for the fertilizer you were showing, if we blend the fertilizer, whatever it needs, use it as same spreader, will it consider as a split plot or not?
I mean, if you can blend them and then apply them on one of these two, then you wouldn't require a split plot necessarily. But here in this case, one fertilizer is dry, the other is liquid, and we're applying them with different equipment. So we're not, yeah. In this case here, we have that limitation, but if they can be blended and you can use just one of the two, then that could be done as well. I mean, that would not be a split plot then if you can blend and apply with just one size of equipment. Awesome. All right, so the 2 points here is first, when one of the treatment factors requires more experimental material than the other. And the second part of that, of when you need a split plot, is that you do not have enough experimental material to have all the plots to be the size of the largest requirement. So an example here would be if we could potentially have all plots to be the size of 12 rows. So all plots would be large. With that, so if you think of it, let's say for the potassium 30 and nitrogen 100 kilos per hectare. If you have large plots that are the size of the potassium requirements, then you would have one pass of that potassium spreader and then 3 passes of the nitrogen applicator, right? Because nitrogen is 4 rows, potassium is 12, so we would need 4 passes of the nitrogen to cover the entire plot of potassium. If you could do that, if you have space for doing all that, then even though you have a mismatch between size of equipment, you would not need a split plot. Normally, a split plot is required when you have that mismatch of how much room you need or how much material you need for different factors, and you do not have space or time or whatever to have such a large plot for everything in your field. So you kind of need to match those two requirements for a split plot to really be useful. So in that case, if we were to do all plots being 12 row with 1 pass of potassium and then 3 passes of nitrogen, we would need 432 total rows planted on this field. I know that, that number, I guess you don't really have to try and imagine it. It's just for us to put a number on how much area we would need to have all plots to be 12 rows in this case. However, perhaps that would require more land than we anticipated or planned for, because maybe when you made your initial calculations, you were planning for plots to be of size 4 rows. And so we really only planned for 144 rows total, but now because of this equipment limitation, we need 432. So we do not have that space. This is how that would look like. So we planned for the study that you've already been seeing a lot, which are these 36 small plots. Now, each one of these small plots are only 4 rows each. So we will need 3 of them to make 1 plot of potassium. Meaning that we will need this much area now instead of this much area for 1 block only. So as you can see, we're requiring more area than we were allocated, than we have access to. So this is a limitation. We do not have all this extra area below here to have all plots to be the size of 3 original plots that were 4 rows. So again, just to perhaps say this again in a different way. When we plan for this study, each experimental unit that we planned for was 4 rows. Now our farm manager comes back saying, well, I cannot apply potassium in 4 rows. I can only apply in 12. So you need 3 of the initial plots to make 12 rows for 1 pass, 1 treatment, 1 experimental unit of potassium. In that case, if we do that and then we apply, so let's say this would be 1 potassium rate, and then each of our original plots receives 1 nitrogen rate. So 100, 100, and 100 kilos of nitrogen per hectare. So 3 passes of nitrogen to make up 1 pass of potassium. Then we need all this extra area that we did not plan for, that we don't have access to. That's the issue. So when you have a mismatch of how much area treatments require, and you don't have that much resources to allocate all this, that's where a split plot comes in handy. So before I move from this concept or keep going here, anyone has any thoughts or questions? Yes.
Well, it seems like a lot of the examples or that are being given are very like cultural practice oriented for like what is split plot entails, but I guess that's just how we're looking at when split plot is needed, not like, because a treatment could be indicative of like a split plot design, like, let's say you're looking at cultivars broccoli, you're testing like 4 cultivars,
Mhm.
and then you decide that half of all your plots are gonna get fertilizer and then half aren't. Like, with that treatment of fertilizer, your main treatments are like, maybe let's say like 4 different cultivars, that overall fertilizer treatment, would that be like split plot design that would be needed for that?
Okay, so let me repeat that online. So Zach is asking here, so we're thinking about cultural practices as being the limiting factor that give us requiring larger plots. Give the example of like 4 broccoli varieties and like 2 fertilizer rates, right? Is that what you're saying? And then you're asking if that would be a split plot or not. So the way that we should think about it is, what is the minimum size of your experimental unit? Right, so let's say, so this would be something you plant on the field. Is that how it would be done? Yeah, so let's say with broccoli, I mean, what is a typical, like, so in this case here, let's say in corn or cotton or peanuts, normally our plots are 4 rows. That's pretty common. Sometimes they're 8, depending on what you're doing, but 4 rows is pretty typical. What would be a typical number of rows per plot for broccoli?
Let's say 1.
1,
Because
okay.
sometimes- Yeah,
So 1 row and what length? Like how many feet? For us, it's normally like 20 to 30 feet.
yeah.
Yeah. Okay, so in broccoli would be 1 row. So just 1 row of that certain variety, and then like 20 or 30 feet long, right?
Yeah.
So that would be the plot. So then the question becomes, can you apply nitrogen at that scale? Can you apply different nitrogen treatments to 1 row only? Because if you cannot, if your equipment says, or maybe if you're doing by hand, you could do whatever, but if you have an equipment that is applying nitrogen maybe to 4 rows at once, that would be a case for a split plot.
Okay.
Because then you have one of your treatment factors requiring more area than the other. However, if you can apply nitrogen to that 1 row, perhaps by hand or some other way, then you don't need a split plot, right? Because then you can this row can have 100 kilos of nitrogen, and the row right next to it can have a different rate, because you don't have that limitation of how much footprint you need for one of your treatments.
Okay.
Does that make sense?
Yeah.
Yeah, so again, for you to need a split plot, you have to have a mismatch of how much area, space, time, any resource that one treatment factor requires being more or less than the other, and the fact that you don't have all those resources to allocate. So if we had all this area here, so if all of our blocks could come all the way down, we could decide to just not do a split plot and just do an RCBT just like before, because we have the resources, right? A split plot is when you have some limitation of the resources, and then we're going to try to accommodate all this with the area that we have. Yeah. Yes, Sabir.
So from this, is a split plots a design that we choose to do, or is based on our situation?
Yes, that's a great question. So split plot is basically that's when split plot has a foot on experimental design, because it's not something that you right off the bat you say, I'm going to do split plots, because that, as we're going to see later, is not the best. So really, for your study to have the most power possible, meaning for you to have the most chance of finding treatment differences, a full RCBD with the whole area would be the best. By doing split plot, we're going to face a compromise, and you're going to see, we're going to talk more about that in the next slides here. But we're going to have to face a compromise between how much power we have on the potassium in this case versus on the nitrogen. It's going to be different. If it is a full RCBD with the whole area, the power you have to find differences for nitrogen or potassium is the same. On a split plot, it's not. They differentiate. And then there's a trade-off in relation to that. So normally, unless you really know, like, oh, I know that this treatment that I apply is always a split plot, because like if you work with irrigation, it's really, really common that irrigation treatments on a field scale are a split plots, just because it requires a larger area. And so, unless you know, like, oh, I've worked with irrigation, everything I do is split plots, then you kind of already anticipate that your study will be a split plot. But normally we don't want to do a split plot if we can avoid it. This is just a design to help us accommodate limitations and still do the best we can, but it's not, you're going to see in a second here, if you can avoid it, you're going to be more powerful, especially with your larger treatment here with potassium in this example. So if you can avoid it, it's better. But the thing is, we always have some type of limitation, either money or space or time, and that's when split plot comes in handy because it still allows us to do a valid design while incorporating limitations.
Okay, so a follow-up. I mean, sometimes you read a proposal and then it just says they will use split plots. I mean, irrespective of the conditions, I don't know if that is the right thing to do.
Yeah, I guess it depends on whoever's planning it, right? I mean, what I can tell you is I can provide you some recommendations of how to approach this on your side, but then what other people do, it's going to be up to them. Maybe they do have a limitation they're just not making clear on the proposal, or maybe, I don't know, maybe something else is going on that they're just been doing that way and that's how they do it. So it's kind of, what I'm trying to tell you is if you do not need a split plot, then do not use it, right? This is just a tool in your toolbox. If you do know that you have a mismatch in how much material you need for different factors in your design, in your treatment design, and you have the limitation on using the total resources that would require for, in this case, potassium, then split plot is what we would use to accommodate for that. But if you do have this whole area, you do have the money for all the seed to plant for the whole area, all the fertilizer and everything, then that would probably be a better study. If just do a randomized complete block design, it's just a larger study. Awesome. All right. Okay, so one key difference here, one key component of a split plot is that now there is an extra limitation on randomization that was not there with the randomized complete block design. So this, we talked about how you would so if you have the design that we've been working with until now, like a randomized complete block design, in that design, our treatments were crossed, meaning that there was no hierarchy between potassium and nitrogen. They were always being randomized together, and a given rate of potassium, a given rate of nitrogen, any of them could happen together, and they were applied together on the same plot, on the same scale, which would be this, right? So if let's say this, if we had all this area for all blocks, I'm just showing for block 1, but if we had it for all blocks, then we would apply, this first block, or sorry, this first plot in blue would receive 1 potassium rate, and then we would have the same nitrogen rate being passed 3 times to match that scale. This would be a randomized complete block design, just like we've been doing. The analysis will be the same. The fact is just that on the field, it would have been a larger study, but on the analysis, it would still be a randomized complete block design without structure between nitrogen and potassium. Now, if we have to do a split plot because we're still contained to the area that we initially asked for, then this is a 2A factorial still, however, in a split plot. So what that means is that now we're going to have a whole plot. This is very key nomenclature for split plot designs. We're going to have a whole plot treatment factor, which is going to be the treatment factor that requires larger area, more resources. That's why it's on the whole plot. So now we have 2 plot sizes, the whole plot, in this case for potassium, and then we have the split plot treatment factor, in this case is nitrogen, with the 3 nitrogen rates. When you see on papers people saying they use a split plot, they have to tell you what is the whole plot treatment factor, what is the split plot treatment factor, because that makes a difference. That makes a difference on their analysis, on the power of the analysis, and on how errors are associated with different means. So you have to tell what is a whole plot treatment factor, what's the split plot treatment factor. We still have all of our potential 9 combinations, but now we have this structure where the whole plot is potassium, split plot is nitrogen. And as you saw on the previous map, they are happening on a different scale. So potassium requires 12 rows, nitrogen requires 4 rows. We're going to use that to our benefit in a split plot. All right, so you know, again, this is kind of that place where split plot has a foot on experimental design and a foot on treatment design. So you cannot just say I have a split plot and period. That by itself does not hold because you have to have that split plots incorporated into an experimental design, which could be a CRD, it could be a completely randomized design, or it could be a randomized complete block design, or maybe even other more complex designs that we're not covering in this class. So here, assuming that we do have heterogeneous experimental material, like a different soil type, as we've been using for until now with our CBD example. So assuming that we still have that heterogeneity on experimental material, we do need blocks. So we're going to have our experimental design is going to be a randomized complete block design, and our treatment design is going to be a two-way factorial split plot. This, take it out of the way. All right, so how does randomization now happens? We're gonna start off with the randomized complete block design idea that each block is gonna be randomized separately, but we have an extra limitation now. So first off, the first thing we do is we randomize the levels of the whole plot to each whole plot in the blocks. So before we just had small plots and we just randomized whatever of our 9 treatment combinations to any of those plots inside the block. Now we first randomize the whole plot treatment factor, which will look something like this. So we know that on the smaller plots that we first planned, the 4-row plots, the black ones, we need 3 of those to have 1 plot of potassium. So as you're seeing here, so block 1 basically only has 3 whole plots. The whole plots would be these rectangles with different colors, where different color represents a different potassium rate. So we take block 1, we randomize potassium 0, 0, 30, and 60, I think were our levels. So we first randomize those in block 1, and then randomize just potassium again on block 2, and then just potassium on block 3, and just potassium on block 4. And notice that we have 3 whole plots per block, right? So we have only 3 potential plots inside of that block for potassium. So this whole thing here is 1 plot for potassium, and then a second plot for potassium, and a third plot for potassium. Then, once you randomize your whole plot treatment factor, which in our case was potassium, you come back and you randomize your split plot treatment factors within each of your whole plot treatments. So we randomize your nitrogen levels inside each of your potassium plots. So we have a whole plot for potassium, and now we're going to come back in each one of those smaller cells and randomize 1 nitrogen within that, which is going to be something like this. So let me just zoom in to kind of show you. So our first randomization on block 1 was for potassium. Where is the dotted line? So maybe let's say that this blue dotted line here was potassium 60 kilograms per hectare. Then we come back inside of this blue rectangle and randomize nitrogen within those smaller plots. So this is probably, I don't know, 0, I think we had 0, 100, 200 maybe, don't remember. But the nitrogen levels are then randomized individually for each one of the whole plots. So this is a randomization for nitrogen, which is separate from this randomization for nitrogen, which is separate from this randomization for nitrogen. And every nitrogen randomization is separate within that whole plot size. Any questions? I know this can be a little bit confusing, so I do want to give you all some space and time to digest what I just said and ask any follow-ups if you have. So notice that now we have, so before with just RCBD, well, let me trace back all the way to CRD. So with CRD, we were able to have 4-row plots, which is the smaller cells, right? 4-row plots for everything. And we did not have any restriction on randomization, right? We did not have blocks, meaning that maybe by random chance, Perhaps all the potassium zero, nitrogen zero treatments could happen just all three right next to each other by random chance. It would not be a really good random randomization, but it would still be one potential outcome, right? It should be random. So CRD, no limitations on randomization. The next step on the complexity is RCBD. You have some limitation, in this case here, lack of homogeneity of experimental material. That is our single limitation here. You do blocks, and then because you have blocks, then you are randomizing within the blocks. So we have one randomization restriction if you're just using an RCBD. Now we're bringing another level of complexity where we have still our soil property differences, and therefore we still need randomized complete block design, but we also have an equipment difference that requires more area that we don't have. So we also have a space restriction, in which case a split plot can help us to handle that, right? So one thing to notice now is, like in block one, you have one big, so if you think of it, potassium is happening one time per block, right? We have one, let's say this is potassium 0, 30, and 60. Now nitrogen is happening 2 times per block. Each level of nitrogen is happening 2 times per block because, or I'm sorry, 3 times per block, because it happens once in each level of potassium. So we still have replication because I still have, let's say that this dotted blue line is potassium 0. So I have potassium 0 here, I have here, and I have here. So I have replication 3 in this case, or 4 because it's 1 per block, but then nitrogen has more replications, right? Because I have in each block nitrogen, one given nitrogen rate. Let's say that this is the 100 kilos of nitrogen. Is appearing 1, 2, 3 times per block. So nitrogen has more replications than potassium. And this is going to reflect on the trade-off of power between the power that we have to find statistical differences between potassium and nitrogen is going to change on the split plots. All right, any questions about this?
Are we gonna go deeper into the loss of power?
Yes,
Okay.
we're gonna, yeah, when we look at the ANOVA table, it's gonna be more clear of why that happens. So we're going to 11:30 today. We're reaching 10:30. I think I'll go through this slide, or maybe this is a good point to take a 5-minute break because this slide connects to the ANOVA table, which comes afterwards. So maybe let's take a 5-minute break if you need, and we'll come back here in 5 minutes to continue the lecture and then start the exercise as well.
It might be like, the chance of winning is pretty high on that. But most people can bring like this.
All right, so let's resume our class. Again, if you're online, make sure to turn on your cameras. Okay, so let's look at, I always like to show you the effects model because I think that may help you to understand how this trickles down into an ANOVA table. I know some people may make sense of the model itself that is required for them to understand. Some people look at something like this and run away from it, which is okay, but I would just wanted to provide both of those. So we still have so Yijk is going to be our observation. So in this case, yield. It's going to be that yield coming from a specific block, specific potassium plot, specific nitrogen rate plot. We always have our overall mean in this ANOVA table. Rho K is our random effect of block, just like we had before. Now we have alpha I, our effect of potassium rate. And now it's something different. I want you to pay attention here. The interaction between potassium and block, which is that alpha rho IK, is the whole plot error. Now with a split plot, we're going to have two levels of error. One of them for the whole plot, another for the split plot. This does not happen with the plain randomized complete block design. So this is something to pay attention because we need to make sure we understand what we're doing and we specify this in code as well. Now, after that whole plot random error, we have our beta J, which is the effect of the nitrogen rate. We have the interaction between, so in this case, alpha beta is the interaction between potassium and nitrogen. Something interesting to notice is even though your potassium rate main effect has that whole plot error that is testing that potassium effect, but nitrogen and the interaction of nitrogen and potassium are at this lower level on this hierarchy here. So not just nitrogen, but also the interaction of nitrogen and potassium are going to be lower in this hierarchy between nitrogen and potassium. So alpha, beta, IJ are the parameters for the interaction between nitrogen and potassium. And then we have our EIJK, which is the residual of the model. So we have the residual. This is our residual error that we're going to be using that to test the effect of the interaction between nitrogen and potassium and nitrogen by itself. And we have this whole plot random error, which is what we use to test the effect of potassium. Now looking to ANOVA table, just giving you some explanation here. So lowercase n is the levels of nitrogen, so we have 3. Lowercase k is levels of potassium, we have 3. R is number of blocks, we have 4. And uppercase n is total observations, we have 36 still. All right, a lot of stuff going on here. We looked at this ANOVA table for the previous designs already, but let's just walk through this ANOVA table here and understand what is going on. So just like on the model, we have the block effect. We have 3 degrees of freedom. We have the sum of the squares of the block. So remember the sum of the squares, you can think of it as the amount of variability in the entire data that is being explained by that line. So in this case, how much variability is explained by block. We have our potassium rate, so sum of squares of potassium. And I guess in this case of potassium and everything else below it, we have a sum of squares, and then we have the mean squares, which is just dividing the sum of the squares of that line by the degrees of freedom of that line as well. So the mean square of potassium is just the sum of the square of potassium, which is this, divided by 2, which is the degrees of freedom for potassium. Then we have the whole plot error, which is just that interaction between potassium and block. This has a given number of degrees of freedom. It has a formula there if you wanted to calculate, but this comes down to 6, meaning that the error that we're going to use to test potassium, that error has 6 degrees of freedom. And then when does that become important is that, so we calculate an alpha ratio, which is just the division between the mean square of your interest on the numerator, which in this case is potassium, divided by the mean square of the error associated with that. In this case, I want you to notice that, so before, if we were to go back to the ANOVA table on the randomized complete block design, on the F ratio, the denominator mean square that we're using was the same. It was the same for nitrogen, the same for potassium. We have the same power of finding differences because of that in a randomized complete block design. In a split plot, we have two levels of error. Whole plot error is the interaction of potassium and block, which creates the mean square of the whole plot level error, which is what we use then to test the effect of potassium. Okay, so kind of let's just like wrap that part of it. We just talked about the whole plot part of this study on the ANOVA. Now let's go to this split plot part of this analysis. So we have nitrogen rate, which still degrees of freedom is 2. Sum of squares of nitrogen is just how much variability is explained by nitrogen. We have the mean squares here is just dividing sum of squares by degrees of freedom of nitrogen. So up until mean squares, we're all only talking about this row. I guess before I tell you about the F ratio of nitrogen, let's just go lower on this ANOVA table. So nitrogen rate main effects. Now the nitrogen potassium interaction effect. Similarly, we have degrees of freedom, we have sum of squares, we have the mean square, which is just that divided by that. And then we also have an F ratio. Before I look into these F ratios here, I just want to tell you about this split plot error term. So the split plot error term, there's another formula to calculate that. And that, if you just follow plugging all the numbers, has 18 degrees of freedom on that. And where the repercussion of that happens is, notice that on the F ratio that we do for potassium, nitrogen, and the interaction, for nitrogen and the interaction, which are at this split plot level, these mean square effects of nitrogen and interaction are being tested, are being divided by the mean square of the split plot error, which is this one right here. So a quick wrap up. Potassium rate effect is being tested by the error of the whole plot level, which is this one here, and it has 6 degrees of freedom. The split plot level effects of nitrogen, main effects, and interaction are being tested by the split plot error, which is this one here. It's the different one, and it has a different number of degrees of freedom of the error. So we have two different errors testing different parts of this design. And this is a key difference because you do not have this on a plain randomized complete block design. Now, perhaps I briefly mentioned that one of the implications of this is that you're going to have more or less power depending if you're testing your whole plot or your split plot treatment factor. Given what I told you about this ANOVA table, which of the whole plot or a split plot you think you're going to have more power and why? Take a quick second to think about that. And if somebody wants to tell me their thoughts, share their thoughts, you're welcome to. Jonathan, you have anything? The whole plot's going to be what? More or less power? More power on the whole plot. Why do you think that?
Less degrees of freedom, so I'm pretty sure.
Yeah, it can be a little bit confusing, but so what happens here is the degrees of freedom of the error are going to be first used here on the mean square of the error, right? So this mean square here, so the more degrees of freedom you have here, the smaller is going to be the mean square of the error. And so the smaller is this value here, the larger the F ratio would be. So really what we want here is, if you remember, every time you have more degrees of freedom in the error, that's a good thing. And one of the ways to get that is to increase your number of replications. So if we were to, for example, increase our R which is our number of blocks here. So if we increase R, that would be an easy way to increase all the degrees of freedom of the errors here. So that's why having more replications increases your degree of freedom of the error, which makes your errors smaller. So you can kind of think of this as like, if I have 2 reps, you know, and I just take those 2 values and take the average and the coefficient of variation of that. And now we have 100 reps. Your mean may not change as much, but the error around that mean is going to be smaller the more reps you have. Perhaps that's an easier way to think about this. So the more degrees of freedom we have on the error, the better. The more power we're going to have to test treatment differences on this design. So going back to what Jonathan was saying is actually the other way around. So we're going to have more power on the split plot treatment factors because we have more degrees of freedom of the error at that level. And this is connected to the fact that on a block level, we have 3 potassium, or we have a given potassium rate happening once in a block. So it happens once in block 1, once in block 2, and so on. But each nitrogen level is happening 3 times per block, right? So this comes back to that as well, to that visual layout that we saw before.
So, but you mean like, if we're looking at a split pot and we like then make the assumption of using like doing it as a whole plot, that's when we lose the power. But if it was a whole plot design, if it was able to be a whole plot design and you looked at it as a whole plot, it would have more power than if you looked at that as a split plot.
Yes.
Okay.
Yes. So, and we're going to get to that point here, maybe in the next slide. But basically, if we could have run the full study with a 12-row plot, so the plot level the potassium requires, which is more than what we have. If we could have run that study, then that study would have the same amount of power to test both nitrogen and potassium because there's no hierarchy between them. They're at the same level of importance. And that design would be the most powerful that we can do if you do not have a limitation of space. Now, if you do have a limitation in space, then compared to that huge design, huge study, a split plot is going to have less power on the whole plot and more power on the split plot factor. But overall, if you look into the overall power of a split plot, it's going to be lower than a full design without that structure. All right. Any other questions or thoughts around this? Mhm.
This here, if we have replication, but we still have the same number of work, right? Or is it work dependent on replication?
Yeah, so perhaps that's so Charles is asking here that he's a little bit confused about replication and block. Perhaps it's really, so when it comes, and this is why it's really, I think it's really interesting to think that, or to understand that in a randomized complete block design, that is normally your replication if you just have a randomized complete block design. But in our case, that we have a randomized complete block design with a split plot design, we actually have 2 levels of replication, right?
Yeah.
So we have the level replication of the whole plot, which again have 1 potassium rate happens once per block, right? And then we have the level replication for the split plot, which happens, so a given nitrogen rate happens 3 times per block, right? So then now just saying replication, I mean, there's still a way that we refer to this. So you would still say that you have 4 blocks, but this is one of the cases where block and replication can be ambiguous because although your number of block is not changing, it's still 4, but the replication number you have is going to depend if you're talking about the whole plot or the split plot level, right? So that's why replication is like this general term, but then the way you would explain this is still would be, I have a randomized complete block design with 4 blocks with a split plot treatment design where potassium is the whole plot treatment factor with these levels and nitrogen is a split plot treatment factor with these levels. So as long as you explain that, if the person knows what is a split plot and how that is designed, they would understand, they would know what you mean, right? Yes, Comfort.
Yeah, so I have a question that's not very clear concerning this block and the whole split plot. So I had a project which we were kind of restricted with the number of growth chambers. So I had like 4 temperature treatments and I had like another cultivar. So we had just 4 growth chambers. So each growth chamber was assigned a temperature treatment. And within the growth chamber, we had the 2 different cultivars. And since they were potted plants, we kind of considered the pots experimental unit. So we had 5 plots. Then we said those were like 5 replication. But then it was repeated twice, which was like considered to experimental run. So it kind of doesn't, it's not very clear to me in the sense that I feel like the temperature treatment should also be like, is it replicated multiple times, right? More than twice. So is that like a split plot also?
Okay, so let me just try to quickly summarize what you said and then give you my understanding and thoughts about it. So if you have a study where you have different temperatures being applied to a growth chamber, and inside the growth chamber you have different, did you say varieties? Like variety of a given plant of a given species. So that would be the perfect example where your growth chamber is basically your whole plot. As long as your variety, you're randomizing within the growth chambers. So we don't have always variety A on top and B on bottom. You randomize that, right? That it has to be randomized to fulfill the assumptions of how you would randomize a split plot. But that would be a great example as well. So let's say if you have 4 temperature treatment levels and you have 4 growth chambers. So you have all of your growth chambers in front of you. You randomly assign the temperature to them. And then within them, you randomly assign if top or bottom shelf is variety A or B. This is a block for you. And then as you run that again, which ideally you would re-randomize everything again, if you run that again, it would be over time, that would be the second run, maybe the next week, is going to be your block 2. And then if you run again on the 3rd week, it's going to be block 3. So that's also a split
So
block, as long as you
yeah, so ideally we should have more than 2 blocks, right?
Yeah, I mean, 2 is the bare minimum, right? So,
Okay.
but I guess in your case, because you can repeat in time, over time, right? You can run 2 and see, what you find from that. And if you think you need more power for you, it's easy to just say, oh, let me just rerun another week. Or I guess I'm assuming it's easy. I don't know if it is, but it's not the same with when you have a limitation in space, right? Because in space, like if I don't have space on the farm, there's nothing I can do, right? I cannot just have more space next year. It's going to be a completely different set of variables impacting. So yeah, in your case, if you have 2 and then you run an analysis, you check what's significant, what's not. If you think you already found the differences you were looking for, great. If you think you don't have enough power yet, you just run another run, incorporate that data, and just, yeah, that's an easy way to, I guess, check your power as you move along.
So it's a right setup.
Yeah. Yeah, that's a great example.
Thank you.
Thanks, Albert.
Because that means, we consider growth chamber as a source of elevation.
Can you say that? I missed the second part.
Does that mean consider growth chamber as a source of elevation?
No, so Charles is asking, does that mean that Comfort's gonna have chamber as a source of variation? Not necessarily, because the thing there is she is interested in the effect of growth chamber, or I'm sorry, on the effect of temperature, which is associated with the growth chamber. So in our case, growth chamber would be, in our example here, growth chamber would be the equivalent of a plot, right? So actually, if we go back to that drawing, we just change the labels and it's basically the same. So she has a growth chamber that maybe has only 2 plots. So her growth chamber is going to be 2 of these. That growth chamber gets a temperature that's randomly assigned. And then top shelf, bottom shelf are randomly assigned to different variety, right? So it was still, the growth chamber would be the whole plot. The whole plot unit would be the growth chamber, right? In our case, the whole plot unit is a rectangle with the dashed line. So it's still a very similar concept, it's just a different setup. And then for her, each block would be like a 1 day that she runs the whole thing, right? Or 1 week, depending how much time that takes. All right, let me. Okay, so one thing that I have a couple questions at the bottom of this ANOVA table. So we noticed that we have 2 sources of error, and they're used in different parts of this analysis. If we had this as a full randomized complete block design without the split block components, that would not happen, right? We would have 1 error term. And actually, I don't remember now from our RCBD lecture, how many degrees of freedom we had in our error term for the RCBD. I don't remember. But I'm assuming it's going to be for sure more than 6. I think it's going to be maybe
It
less.
was in 20s.
Wasn't the 20s?
Yeah.
Okay. Yeah. But so you notice that there we have 1 error that's testing everything. Here with the split plot, we have 2 errors, and they're used in different parts of the analysis, depending what goes on whole plot, what goes on split plots. Another thing that I've seen happen is, let's say you have 2 treatment factors that you have to apply them separately. Like in this case, we apply first potassium and then nitrogen. And if for some reason you have to use split plots, the way that I've seen people approaching this is to say, okay, I have to use split plot because I have a limitation in space, but I have the choice of which goes on the whole plot, which goes on a split plot. They would rather put whatever their least interest. I mean, of course, they're interested in both because you're studying them, but whatever is perhaps the one that you have the least interest between the 2, or the one you know already a lot more about, to put that on the whole plot. Because again, the whole plot's going to have less power to find statistical differences just because of this imbalance. And so if you have the option to say, okay, I can choose what goes on whole plot treatment factor, what goes on split plot treatment factor, then you would decide to put whatever you're more interested or whatever is more variable on the split plots, because that gives you more power to find differences. Yes.
So I was just gonna ask, bouncing off what you just said, is there ever a situation in which someone determines that they've lost so much power on the whole plot level that it's just not worth doing split plot? Is that the thing?
It could be. So Jonathan is saying if somebody does this and then they realize they lost so much power on the whole plot level, then that is not worth it. I mean, that could happen, right? It depends. It all depends on a couple of things. So one of them is how much variability you have on that, right? So let's say for some reason, whatever I'm putting on the whole plot has less variability on my response variable. So perhaps a good example would be, I mean, I don't know, if you're running this in a controlled environment, then I guess you don't have that distinction. But in the case of potassium and nitrogen specifically, you would have more variability with nitrogen just because it is a more dynamic nutrient, right? It can be lost in so many different ways. It's impacted by water, it's impacted by so many things that nitrogen just has more variability to it because of its nature. Whereas potassium is not as mobile in soil, it's not easily lost in different ways like nitrogen. So you would have less variability in potassium in this case, just because that's the nature of it, right? It's a nutrient that stays around, whereas nitrogen is more mobile. So that would be a way of thinking, if you can choose what goes on split and whole plots, you would prefer to have something that's more variable on the split plot because you have more degrees of freedom in the error, you have more chances of finding differences there. All right, so I do want to show you here, I think this is actually the actual ANOVA table from our data using a split plot model. So I just want to show you that here. So we're seeing here the intercept, the potassium rate, the nitrogen rate, and the interaction. So something that this ANOVA table is not showing that is really key when you're running a design that has different error structure, as far as like one level is testing some of these factors, another error is testing another or others, is to understand the following. All the ANOVA tables that we got in R, they have a degree of freedom column. This degree of freedom column is the degree of freedom of the numerator of the mean squares. So let me go back there. So here you see potassium is 2, nitrogen is 2, interaction is 4. This number is this degree of freedom here. So potassium is 2, nitrogen is 2, interaction is 4, which is the number of degree of freedom of the numerator mean square of that test, of that p-value. So in R, it's telling us degree of freedom is of the interaction between nitrogen and potassium is 4. It's coming from this, which is the degree of freedom of that we use on the mean square of the interaction, which is this. So basically, the degree of freedom that we see on the ANOVA table is on the F ratio is the numerator degree of freedom. So it's the degree of freedom of the mean square of nitrogen potassium interaction, which goes on the numerator position of the F ratio. That degree of freedom is not going to change from design to design because it is connected to how many potassium levels you have, how many nitrogen levels you have. What really changes is the degree of freedom of the denominator of your F ratio, which is the denominator of your F ratio is the error term. This is the degree of freedom that's going to change, which unfortunately our ANOVA table does not give us by default. So for you to be able to know that you ran a model and you want to check to make sure that in fact you're using the correct error terms for different parts here, you would need to have a way of finding the denominator degrees of freedom of that analysis, which I think on the exercise I show you how to do that, even though here is not showing. So what we would like to see here, if we could know what is the degree of freedom of the denominator here. So let's say this is dF numerator. Maybe we have another column saying dF denominator. We would like for it to be, let me just go back and get a refresher. This should be 6 for potassium, and it should be 18 for nitrogen. So it should be 6 on this row, and then 18 here and 18 here. That's one way that you would have to check that you're using the correct model. What happens if you did a split plot on the field? So you did everything we're talking about, but then you come here and you do not specify the correct model. You forget to specify that there is a structure in the error, and you just run as an RCBD. You're basically using the wrong error term to test everything, right? And the way that error term is calculated is going to be different. So you're basically specifying the wrong model, and you should not do that. So I'm telling you about the denominator degrees of freedom because that's one of the ways we have to check if indeed you specify the correct model. All right, so I want to take a quick moment here and ask maybe somebody that has not helped me much yet today. I have a few questions, so I'm gonna ask the first one, and if somebody can help me. So what is significant in this ANOVA table? Let me see. Somebody that has not helped me yet today online. Selvin, what do you think? What is significant here in this ANOVA table?
Looking at the p-values, it's like the interaction is significant, and we don't take into account the intercept, which I'm assuming should be the whole mean, the overall mean. Yeah, but since our alpha is 0.05, just we need to look at the interaction.
Right, perfect, thank you. Madhuparna, based on that, how would you extract means from this model?
So are you asking me?
I was asking Madhuparna, yes. Thanks, Evan. Let me ask. Sorry, go ahead.
Sorry, Dr. West was still figuring out.
No, that's okay. Maybe let's see somebody here in Athens. Micah, what do you think? How would you extract means based on this ANOVA table? Let me ask somebody else. Priscilla. Let me try somebody else. Aitan. That's the overall mean. Yeah, I mean, we always get that, but we don't really. No, I mean, perhaps my question is unclear. So if you look into this ANOVA table and now we're going to EM means, how are you going to, what do you ask for in EM means? Do you ask for the main effects, for the interaction, for both, for neither? Just give it. Interaction, right? Yes. So this is really key. And again, we saw some of this confusion on the CRD, and that's why I'm being repetitive here. So you would always look into an ANOVA table, starting from the bottom of it, where you have the most complex terms. In this case, the most complex is just a two-way interaction. If that is significant, then you should focus on that. You should get all the means for this interaction and then decide how you want to show them. We talked about 3 different ways of breaking down a two-way interaction. That's how you would decide if you want to show everything crossed, so potassium and nitrogen, everything the same level, maybe potassium levels inside nitrogen, or the other way around. But this way, you would not show main effects because they're not significant. You would show the interaction. If this is not clear to you, let me know, because it has to be, because you're going to be asked this again and again. And if you don't learn this, you're going to just be missing points. And I mean, and really the key is not points, is that this is something you have to know as a researcher for your own sake. Powerful.
Yes, my question is, so in the split plot, we are automatically considering the block as a random effect? I mean,
Yeah,
because
so that's a great point. So now we're actually going to be using blocks as random, but for a different I mean, for outside of the conversation of should it be fixed or random, is more from the perspective that we have 2 levels of error. And so the way we're going to specify those errors in the model has to be through the random effects part of the model. Yeah, but yeah, so I guess in short, yes, we're going to use blocks as random. Awesome. All right. Yeah, this is just a little text about that numerator degrees of freedom. Yes, Tifton.
You said you're going to treat them as random effect. Is there a way, like a situation, where we can use them as a fixed effect?
Yes. So in this very specific case here of a split plot, what you're going to see on the model when we get to the coding side is that actually there are some things that are going to be both treated as random and as fixed for different reasons in this case. So what happens here is in the model, we're going to see this. The way that you differentiate a randomized complete block design from a randomized complete block design with split plot is that we're going to nest our whole plot treatment factor, which in this case is potassium, inside block. So that's one of the key differences in the model part. But then you think, okay, I have potassium nested in block as a random effect, but I still want potassium means, right? You're still interested in the means of potassium. So potassium is actually going to appear on the random effect with the goal of setting up the proper error structure of the model, and on the fixed effect because we want to know means. So potassium is going to be treated as both random and fixed in this model. Block will not. Block is still just going to be random because we don't care about the block means anyways. But that's a great question, Paul.
If there would be an interaction significant, if interaction is significant, right? And if one of the main effect will be significant, then we will extract the mean of interaction as well as.
Okay, so Amandeep is asking if the interaction is significant and the main effects is also significant, what do you do? You would still extract and focus your discussion and your results on the interaction, right? Because if you look at the main effects by themselves, even if they are significant, they don't tell the whole story, right? So if you want, I mean, some people would still give you the means of just, let's say if potassium main effect was significant, you may still give the means and say what was different from what, but that should not be the focus of your results, right? The focus should be the interaction because that was significant And the story that you tell with interaction is different from the story you tell with main effects, if they're significant as well. So it's still the most complex. So this design is very simple, but sometimes, like if, let's say if you have a three-way factorial, let's say we had phosphorus rate as another level here, then you would have, on this ANOVA table, you have the three-way interaction, potassium, nitrogen, phosphorus. And you have the two-way interactions, right? You have nitrogen and phosphorus, nitrogen and potassium, potassium and phosphorus. You have 3 two-way interactions. So depending on what is significant where and when and how with who is how you would choose how to show your means. So let's say in that case, if your three-way was not significant, but you have 2 of the two-way interactions that were significant, you would show them separately. Right? So it always has to be the most complex term in the model that is significant. That's where you start. That's why we start from the bottom up. Okay, so the split plot trade-off. We talked a lot about this. I hope that you were able to see that on the degrees of freedom of the errors for the different errors of the split plot study. But the whole plot, so if you compare the split plots, if you compare the RCBD split plots against a plain RCBD, the RCBD split plot is going to have decreased power on the whole plot treatment factor. And it's going to have increased power at the split plot factor. But overall, the split plot study has less power than a full RCBD without that structure in place. So quick summary here. So we use split plot designs most commonly when your different treatment factors require a different amount or level of experimental material. And especially if you cannot accommodate that, right? I mean, they require different amounts and you don't have all the amount to do a full study, in this case, according to potassium, which is the one that required the most material. So that's where a split plot comes in very handy. And in a split plot, the one thing that sets it apart is how we randomize things. So we're randomizing things by first randomizing the whole plot and then the split plot factor inside of the whole plot factor. So there is another limitation on randomization. And because we're randomizing at 2 different levels, first the whole plot, then the split plot, that creates 2 different error terms in our model, and they're used differently on the ANOVA table. So we need to make sure that so I hope you're seeing that, like, because a lot of times, you know, some students may come up and they may have like, you know, oh, I have this study that happened. Can you help me to understand what is the design or how it works, how I should analyze? Something I'm hoping that you're getting from here is you need to know what you're going to do from the planning stage, because then that makes sure you're randomizing things appropriately. You're putting the thought into how you're randomizing things given your limitations, and then that trickles down later to the model you use to analyze the data, right? So sometimes, I mean, I had students come up and say, hey, I have this, how we analyze this? And then I asked, how did you randomize? How did this work? How was that assigned to that? And it was not random. It was just, you know, I mean, I guess it was not random, or maybe there was something there that did not follow, you know, the appropriate conditions we would for a given design. In that case, then it's like, well, we don't really, I mean, it looks like a split plot, but it's not really because you did not randomize this or that. So with all this talk, I'm hoping that you're understanding that we have to be aware of these things from the planning stage all the way to the analysis stage, because it all connects, right? You cannot just make up a design after you have done it and say, oh, I'm going to treat this as CRD, or maybe I'll try a split plot. No, it is what you did on the field, and that cannot be changed. You cannot go back in time. So making sure we do the right thing on the field and then analyze it appropriately later are 2 key parts of it. And then a quick summary as well, that we talked about this loss of power overall on a split plot compared to an RCBD without the split plot. Okay, so this wraps up the lecture. We have 15 minutes, not enough time to start an exercise, but I want to tell you about a couple things. So I shared 2 scripts with you this morning before class. So if you have not pulled yet from GitHub, if you do the pull, we're going to get 2 new scripts. We're going to use one of those scripts for next class. We're gonna code, is gonna be the code for this analysis, for this plot analysis. And I have another script there that's gonna be associated with an assignment. So the one with the assignments, even though I have pushed the assignment already, but I was not able to finish writing the assignment instructions. So right now the assignment instructions are not complete, so do not start that yet. Wait until I tell you to do so, which is going to be today. But I basically am going to ask you to watch on your side and code along on your side the randomization of the split plot exercise in R. So we're going to do that for this design. So first part is watching the video, coding along with me, doing it on your side. That is just you learning how to do this. And then the assignment, I'm going to ask you to not use the data we're using in class. I'm going to ask you to either use an example from your experience, maybe from a paper, maybe from your head. If you want to come up with something that you haven't even seen, but I want you to basically tell me a specific treatment factors and levels and randomize them in a split plot manner. It could be applied to your own area of expertise, does not have to be field research. It just cannot be nitrogen and potassium rates. That's all that it cannot be. But it can be really anything, does not have to be crop, can be food science, can be whatever. It just has to be, you have to tell me what are going to be your two treatment factors, which one goes in the whole plot, which one goes on the split plot, what are their levels, and then I want you to randomize those things and make up plot layouts for that. That's what I'm asking you to do. Again, you can use something maybe from your own research. You can, if you know of a paper that have done this, all you need to know is, again, what are the treatment factors, the levels, how many reps. That's all you need to get from a paper. So you can look for that in the literature if you need. And if you wish to just make something up from your head, that's completely fine with me as well, as long as it's not the same as we're doing in class. But that's going to be an assignment for you to complete around randomizing a split plot design. So I guess before we wrap up for today, I want us to get started and be ready for next class. So this is going to be a time where we're going to create a full new project, which involves creating on GitHub, cloning that to your local machine, creating the subfolders, doing all that, right? So what normally I would send you an email saying, create this exercise. We can do that together here if you want a refresher. So we do have a lecture that where that was very, very detailed, with very detailed instructions on that. I think it may have been this. Let me check. Yeah, this is the one. So this is the January 21st. That's the lecture that, if you want a refresher, we're gonna be using this more frequently from this point on. So if I tell create a GitHub workflow for a given exercise, then I want you to walk through these steps here. What we're gonna do is create a GitHub workflow for an exercise called 05_SPP for a split plot. So I'm gonna do on my side because I don't have it yet. You can do on your side as well if you wish. Because then if you have questions, I can help you out. So remember that we start on GitHub, that's the easiest way. And then we clone that to your computer through RStudio projects, and that's how we set up. So let's create new here. I'm gonna create the name. Is gonna be, well, sorry, maybe I went a little bit fast. If you were on your GitHub profile, you basically go to your repositories, and then you're gonna click new to create a new one right there. I want to call this 05_SPP for split plots. In my case, I already have one called 05SPP. I'm gonna add a _25. You don't have to, just a reminder. Keep it public. Let's add a README file. Let's choose a git ignore for R. You just have to scroll all the way down and find R. You can leave no license and then create a repository. Remember that this is something you're creating on your GitHub. It's not my GitHub, right? You're creating on your side. Once you create that, it should just show you the REPL initial page. We're going to come here on this code green button and copy the HTTPS, which is already what's there. You just copy that by clicking on this button. Now we're going to come to any RStudio window. It can be, if you had one open already, could be that. If you don't, just open one. Once you have RStudio open on the top right, we're going to click on that button and ask for a new project. Again, all these instructions are on the lecture. If I'm going too fast, you can follow up later if you wish, but they're all in there. We're going to choose the option version control. We're going to choose the option Git. And then we're going to paste our repository URL, which is what we copied from GitHub right there. And then on the browse button, I want you to click on browse and look for the class folder like this. So you should be seeing the 01 intro, 02 wrangling, and so on. Do not go inside of any of those folders. You want to be at the level of the course main folder. So if you're there, click open. If you're not there, navigate to that. And then create project. That basically prompts RStudio to create a whole new RStudio project where it has cloned your GitHub repo for you, so you don't have to do that manually. And already opened up for me 0405 SPP 25, so it should have done that for you. If you check on your file system where you asked to save it, it should be, so in my case here, 2025 CRS 8030. I now have a folder called 05 SPP 25. It should be there. That's what GitHub and RStudio did for you. If you go in that folder, you'll just have the rproj and the README. So as you know, we're going to create the subfolders data, code, and output, as always. So this was the project on your side, on your GitHub, and you cloning that for you. Now, maybe you've done this already, maybe not, but you would go back then to your 2025 DSA. You have an RStudio project in there, so you're going to click on that. I don't have, so I'm not going to be able to show fully what it looks like on your side. But once you open that RStudio project from the 2025 DSA, you just click on the Git pull button, which is then going to pull all the files that I uploaded to that GitHub repo, which is a different one, right? It's not the one that you just created. You do a pull, those files come to your computer, then you can go back to your folder just like we were before, and you should see those files on the folder 04 class code. So I have a SPP mixed partial, which is what we're going to do in class. This is not the assignment. This is in class. The assignment will be the SPP randomization partial. So randomization is what you do on your assignment, and we're not going to go through that in class. I'll share with you a video from last year, and we're going to basically do that. You're going to do that on your side as an assignment. If you're able to do all this and you want to be fully ready for next class, you can just copy here the script SPP mixed partial, the one that we will go through in class, next class period. You can copy that from your 04 class code and then just navigate to your 05 SPP and paste inside of code. Once you have done that, what I would say is let's go ahead already and do a git stage, git commit, and git push. So the new changes you've made to this local repo are reflected on your GitHub. So if you have the 05 SPP RStudio project open, you already know you can just click on that code folder to stage it. You don't have to stage the rproj if you don't want to. And then we're going to come on the check mark, which opens our commit panel. You just write a message. It could be, added partial scripts for SPP, for split plots. You commit, should have worked all right, and then you push. So do a git push, and that reflects your changes to your GitHub repo. So now, if you were to go on your GitHub, so online, which I'm doing here, if you refresh that, you should now see the code folder with the script that you just included in there. So this time I did want to take the time to go through this with you in class, because it's been a while since we've done this. I wanted just to help you to, as a reminder, as a refresher. In the next exercises, I'm just going to tell you, create the exercise 06, whatever it is. I uploaded the script to GitHub. That's it. I'm not going to walk you through every single step again. You're going to do that on your side before we get to class, so we can start coding faster and not spend time with this. All right, so I think Amrinder may have opened the attendance issue. So claim your attendance. If you do not have any questions, you're dismissed. If you have any questions, I'm going to stick around for the next 5 minutes to help anyone.
Professor,
Give me just a second.
I have.
Give me just a second, Omar. Let me just stop recording and then I'll be right with you.